So yesterday when we left off, we had gone over naming of ionic compounds, or writing the proper names for ionic compounds. We looked at the very basic ones, which was review from last year for you. And then we looked at ones that contain multivalent metals. That is, metals that have more than one possible charge, okay, and how we write their names. So I'm going to put two examples up on the board here. I want you guys to try them as a bit of review. And then we have one more thing to do with ionic compounds that will be new, okay, that we need to go over. Okay, so here's our first one. Good one. All right, so there's our first two. I want you to write the proper names of those two ionic compounds. We'll give you a couple minutes and then we'll walk through them together. 1 minute, let's see. All right, let's have a look at these two here. So our first one, we've got Mg, which is magnesium. Okay, and our second element is N, which is nitrogen. Okay, but that'll be put to nitride, okay, because it's got to end in "ide." Do I need a Roman numeral for this one?
No.
I do not. It only has one possible charge. It's 2+ all the time, so there's no need for a Roman numeral. There's the name, magnesium nitride, and we're done. Okay. Our second one, what's Cu stand for? Copper. Does it have more than one possible charge?
Yeah.
Yes, so we are going to need a Roman numeral on this one, so we'll leave a little room for it. S stands for? Sulfide. Okay, so we got that. Now we've got to figure out which Roman numeral does this one need. To do that, we always look to the non-metal, because there aren't any non-metals with more than one possible charge. Okay, so we got Cus, and the S is a -2. All ionic compounds have to have an overall charge of 0, so that means we have to get 2 positive charges from the copper. So this is copper 2. Sulfide. Okay, is that ringing a bell? All right. What would you call this? Polyatomic, yes, that is what you would call it. SO4 is what we call a polyatomic ion. Sometimes people call it a complex ion, and we use polyatomic most of the time because it has more than one atom, right? Poly means many. So when we're naming these, it's actually even easier than the other stuff. It's still exactly the same rules. All we have to do is find the polyatomic ion in the table of polyatomic ions that's at the top of your periodic table. All right, you'll see there at the top it says table of common polyatomic ions. All you have to do is find that polyatomic ion and write its name. Right? So this stuff would be sodium, because that's what Na stands for, and SO4 is sulfate. Okay. These obviously only show up in ionic compounds, because they are, after all, ions. Okay? Table of polyatomic ions, you're never going to see these in a molecular compound, because they're charged particles. All right, everybody okay with that? Okay, so that's how we write ones that have polyatomic ions. We just write the name. We don't change it to "ide." Some people do that. We don't want to. Okay? We write it exactly as it appears. Right? Because if I change that to sodium sulfide, that's something else. Okay? That's Na2S, not Na2SO4. Those are two different things. Right? So I'm going to write a couple on here. I want you guys to see if you can get them named. Okay? Give you a couple minutes on those three. So let's have a look at these ones here. Our first one, we got calcium, Ca, and what's PO4 stand for? Phosphate. Do the little numbers matter for the name?
No.
No, we don't put prefixes in. It doesn't matter what the little numbers are. The little numbers are just there to make sure that the charges are all balanced when you drop and swap. Okay, so this stuff is just going to be called calcium phosphate. Now, what are the brackets for?
Well, that's one unit, so then it shows, so that it will show in that compound that there's two of that one.
Exactly. Okay. Brackets are used in the same manner here as you would use them in math. Okay. In math, you would do, if you had something in brackets, you'd have like 2 in brackets 3 plus 2. Well, that means multiply everything in the brackets by 2. Well, it means the same thing here. It means that there are 2 PO4 ions, right? So that means 2 phosphorus atoms and 8 oxygen atoms in total. Everybody with me there? So that's what the purpose of the brackets is. We only use brackets if there's polyatomic ions because we have to enclose them. They always come as a unit. All right, our second one here. What does Mg stand for?
Magnesium.
Magnesium. Okay, and what's it with? Nitrate. Okay, our next one, Li is lithium. And what's CO3? Carbonate. Okay, so writing the names of these is pretty easy. You just have to look them up. All right, this one's a little trickier though. What's NH4? Ammonium. It is the only positively charged ion. It's the only one that acts as a metal. It's weird because you see a non-metal starting out the compound and you immediately think it's a molecular compound, but it's not. NH4 is an ion, a charged particle, and it is the only one with a positive charge. If it's positively charged, then it's giving up electrons and acting in a metallic fashion. Okay, so this is one of those weird situations, okay? But ammonium is a metal, or acts as a metal, okay? And this would be ammonium chloride. All right, questions on that? Okay. The other way, we've looked at, I give you the formula, you have to write the name, okay? We'll look at when you go the other way here in a little bit. We're going to talk about molecular compounds first, and then we'll look at, I give you the name, how do you write the formula? That's where that whole drop and swap thing comes in, okay? But we'll talk about that in a little bit here. Now we need to talk about molecular compounds. So a molecular compound is only going to contain nonmetals, okay? So it's a different type of bond. Ionic compounds have this ionic bond where electrons are traded, so they're very weak because once they have the electrons or have given up the electrons, they're happy, they don't need each other anymore, okay, that kind of thing. Molecular compounds have what we call a molecular or covalent bond. Covalent means sharing electrons. So these bonds are incredibly strong. Okay, so unlike the nature of ionic compounds where it's like, I got what I wanted from you, I don't need you anymore, this is the 85-year-old couple who still holds hands when they walk. Okay? They are so attached to each other, they cannot be apart. Okay? That's how a molecular bond works. Right? They are going to have to stay together because the only way to be fulfilled, that is have their outer shell full of electrons, is to share an electron with somebody else. All right, so because they have to share them, they don't trade them, they stay together. These bonds are incredibly strong, which is why molecular compounds have a tendency to be less soluble in water. Why their solutions will not conduct electricity. They don't break up into charged particles. Right? For example, alcohol is a molecular compound. Okay? It won't conduct electricity. You put it in distilled water, it still doesn't conduct electricity. Butter is a molecular compound, okay? Doesn't dissolve in water, okay? Doesn't conduct electricity in solution, okay? All of that kind of stuff. So they have very different behaviors, and it's because of the nature of the chemical bond. So looking at water here as an example on the left, we see the oxygen atom, okay? An oxygen atom has 6 electrons in its outer shell. That outer shell is capable of holding 8, which is why it likes to hang out with 2 hydrogen atoms. Right? Each one of those hydrogen atoms has an electron that it can share with oxygen, and oxygen can share one with them. Now, hydrogen's got its outer shell full with 2, and oxygen has its outer shell full with 8. Okay? But they have to stay together in order for their outer shells to be full. So it's a very, very strong bond. Now, question.
Isn't hydrogen a metal though?
It is, but it can behave both ways. This is one of the situations where it goes the other way. Okay? It's behaving as a non-metal here. Okay? Water's weird. If there's a rule, water's the exception to it. Okay? Like things that expand or things that contract when they get cold. What does water do? It expands. You ever put a water ball in the fridge and then try and set it on the counter? Okay? Tips over right away, right? Because the ice expands. Water expands when it freezes. Okay? Pump pops out the flat bottom of the bottle so it's round and it just tips over. Okay? If you try and freeze something that's in a glass container, it'll break the glass. Okay? You'll come back to see broken glass inside the freezer because it'll break it open. Okay? Water expands. That's how erosion works. Okay? Water runs into a crack in a rock and freezes. There's enough force there from the water expanding, it can crack rocks open. Okay? So if there's an exception, water's it. So here's the exception. Hydrogen's a metal, but in water it's not. Okay? It's all everything. When we start talking about the properties of water later in the unit, you'll see we have all these wonderful rules, and the most important substance on Earth is the one that breaks them all. Okay? All right, so 2 nonmetals, they react to form a new substance, okay? Because nonmetals usually have negative charges, we're not worried about balancing the charges. We don't drop and swap these compounds, okay? There's any number of combinations that they can have, okay? There's lots of different ways that, compounds can go together, right? Because they're not trading electrons or balancing charges, they're just sharing and filling shells and stuff like that, okay? So no one gets to keep the electrons, they're shared in those compounds. So when we're naming them, we have to use prefixes. Okay? There's more than one way for things to go together, so we have to indicate. In this particular combination of hydrogen and oxygen, there are this many hydrogen, and there are this many oxygen. Or in this particular combination of phosphorus and oxygen, there's this many phosphorus and this many oxygen by using prefixes. Right, so molecular compounds, like we said, arise when 2 nonmetals arise to form a new compound. Okay, so difference here is we write the first nonmetal with its name unaltered. Okay, so we write it as it appears on the periodic table. The second nonmetal gets its name ending in I. Right, so whatever ends a compound always ends in I if it's an element. Okay, so CS2 would be carbon disulfide. Okay. N2O, this is actually wrong, would be dinitrogen. What's the prefix for 1? Mono. Okay, so dinitrogen monoxide. Okay, everything ends in I. Okay, this example here would be tetraphosphorus decaoxide because the prefix for 10 is deca. You might want to write this down because you don't have it anywhere, but here are all the prefixes. So prefixes are basically the same as geometry. If you're looking at a figure with a certain number of sides, it's basically the same prefixes. 1's mono, 2 is di, 3 is tri, 4 is tetra, okay? 5 is penta, 6 is hexa, 7 is hepta. If you took French immersion, you may have been told septa. That's French. Mr. Real, our chemistry guy, hates that. Hepta, or he'll snap. Okay? Kid you not. Really, it's one of those triggers for him. Okay? Hepta, okay, is one of those. Okay? Is the proper one. Octa, nona, and deca for 8, 9, and 10. Okay, that is something you will have to memorize. It isn't on your periodic table. By the way, you don't have to memorize the periodic table. I know there's like somebody out there who's been telling people that. You don't. I gave you one. You'll always have access to one. The Chem 30 diploma, the Physics 30 diploma, even the Bio 30 diploma data booklets contain a periodic table, that one, okay? So you never have to memorize it. You'll kind of eventually know some of them off by heart because you use them so often, but you don't have to go out of your way to memorize the whole thing or know the periodic table song, which I will not sing because A, I don't know it, and B, nobody wants to hear that, okay? All right, so those are your prefixes. Pretty straightforward for naming molecular compounds. Okay, so let's have you guys try the first 4 here, and then we'll go through them together and see how we do. All right, let's have a look at these ones here. So for our first one, N stands for nitrogen. Okay, so we write that name unaltered, and then there are how many iodines?
3.
Triiodide. Now, you can hyphenate that, and I think according to English rules, you're supposed to when it's a prefix and then it adds on to another word that starts with a vowel. The prefix ends with a vowel and the word starts with a vowel. You're supposed to hyphenate that. So hyphenated, I think that's what you're supposed to do. It looks weird when you have 2 I's right together. Okay. Number 2, we've got carbon, and that carbon is with 4 iodines, so it's going to be tetraiodide. Okay, number 3, I've got how many nitrogens?
2.
Okay, 2, so dinitrogen trioxide. All right, and for number 4, this is tellurium diacetyl. Now, I had a whole bunch on here that were 1s, but I didn't put mono on them. Why? Because it's the first one. Yeah. Okay. We don't use mono as a prefix if it's the first material. I don't know why. Chemists just have to feel important and have weird, tricky rules. Okay. So you don't put mono on the first chemical, okay, or on the first element, but you would put it if it was appropriate on the second one. Okay. Let's have you try the rest of those. We'll go through them together here in a couple minutes, and then we'll look at a mix of both. See if you can use the right naming rules and identify ionic and molecular. Is the first one ionic or molecular? It's ionic. Lithium is a metal. All right, so we apply the ionic naming rules, and this stuff is lithium chloride. All right, no prefixes, no Roman numerals, nothing like that. It's a very simple binary ionic compound. All right, number 2, ionic or molecular?
Ionic.
It's ionic. Chromium is a metal. Does chromium have more than one possible charge?
Yes.
Yes. So this one is going to require a Roman numeral. So this is going to be chromium, and then we'll leave a little space for the Roman numeral, fluoride. All right, I've got to figure out which charge, it's 2 or 3, okay, chromium has here. Well, fluorine is always a -1. There are 3 fluorines, so that gives me a total of 3 negative charges. That means I've got to get 3 positive charges from a single chromium ion. That means that this is the chromium with the 3+ charge, the chromium 3 fluoride. It is very common for people to forget to look for that. Okay? They just see the metal and non-metal, they name it like it's ionic, and they forget to check if it's going to need a Roman numeral. Similarly, people over-apply the Roman numerals and put them on everything. Okay? Don't need them on everything, right? You got to check. If it's ionic, look for more than 1 charge in the box on the periodic table. More than 1 charge, Roman numeral. Single charge, no Roman numeral. Okay, number 3, ionic or molecular?
Molecular.
Molecular. These are both non-metals. So applying the non-metal or the molecular naming rules, this will be phosphorus and tribromide. Number 4. Ionic or molecular?
Ionic.
Ionic, zinc is a metal. Does it need a Roman numeral? No, zinc only has one possible charge, so this will be zinc iodide. Number 5, ionic or molecular? Molecular, it's 2 nonmetals, so I apply my molecular naming rules. Silicon dioxide. And then number 6, ionic or molecular? Molecular. Carbon and sulfur are both nonmetals, so this will be carbon disulfide. Tetra. Di. Sulfide. Tetra. Sulfide. More coffee. More coffee. Okay, how many people are done 7 and 8? Let's look at those two then. What's TC? Technetium, yeah. Okay, it's a very rare man-made element. It's a metal. Okay, it has a charge of +7. It's very strange. All right. So this will be an ionic compound. Technetium iodide. Okay, technetium doesn't have more than one possible charge on here, does it? It's just a 7. Okay, number 8, ionic or molecular? Ionic. Sodium is a metal. But it does have a polyatomic ion in it. How do we know this? Well, there's more than 2 elements in that compound. If there's more than 2 elements, then it's likely, especially if it's got a metal to start it, a polyatomic ion. So I've got to go with my ionic naming rules. Sodium. And then what's OH? Hydroxide. Okay. Sodium hydroxide is a very strong base. If you've ever used that foaming oven cleaner, that's what makes it work. Strong bases can be just as corrosive as strong acids can, and you spray that foam all over the inside and the base eats all the crud off the inside of your oven. All right, how many people have done 9 and 10? All right, perfect, let's just go. Okay, so we've got ionic or molecular? Ionic. Calcium's a metal. We got a polyatomic ion here, so this will be calcium sulfate. All right, what about number 10? Ionic or molecular? Ionic. Okay. K stands for potassium. What is MnO4? Permanganate. Yeah. Hey, potassium permanganate, okay, used to be used as an antifungal. They would like make a solution of it and put it on their feet. It would kill athletes' foot fungus and stuff like that. The downside to this is potassium permanganate is these little tiny dark purple crystals. When you dissolve them in anything, even the oils and moisture on your skin, okay, they make a dark purple solution that very rapidly, especially with skin, stains your skin. Not purple. Okay, the solution will stay purple. But as soon as it dissolves and gets on your skin, it reacts with your skin and stains it dark brown. Okay, now I only mention this because I had this kid when I taught back in Lloyd, and he never, ever listened to me, ever. And he was pasty white, okay, like just pasty, really, really light colored skin. And I told the kids, because we were doing a lab with this stuff, and I said, now remember, use the scoop for the potassium permanganate. You don't want to touch it with your fingers because it'll stain your fingers. He comes over to me with the sample tray and is doing this. I said, Mr. Coder, these are really pretty little purple crystals. And I'm like, yes, look at your fingers. All around his fingers and his thumb, like to the first knuckle. Remember, this kid was pasty white, are dark brown. Like, where have your fingers been dark brown? and it doesn't come off. You can't wash it off. Like short of bleach and sandpaper, okay? Your skin has to exfoliate off to get rid of it. It's basically like if you've ever seen henna done, it's like that, okay? It lasts for a long time. And his fingers and his thumb are this dark brown color for like a week and a half. And you can tell that he was working at it, trying to get it off. But he never listened. Listen when I tell you stuff. Sometimes it'll be important. And if you screw up and it's funny, I will laugh. Okay? All right. Number 11. We got a molecular compound here. Okay, this is going to be nitrogen monoxide, right? Okay, we don't put the mono on the first one, just on the second one. All right, for number 12, we've got beryllium, which is a metal, so this is an ionic compound. We've got a polyatomic ion, cyanide, so this will be beryllium cyanide. Okay, this will be barium cyanide. Okay, same kind of deal. All right, number 14, ionic compound. The metal is sodium. What's HCO3? Hydrogen carbonate. That's baking soda. Sodium hydrogen carbonate is baking soda. And then finally, okay, this one's a trick. People look at this one and they see it on their table of polyatomic ions and they say phosphate. Except polyatomic ions do not exist by themselves, only as part of a compound. But there can be molecular compounds that are the same formula, just not charged. So this would be phosphorus tetraoxide. Okay. All right, is that making sense? Are we kind of seeing how that works? All right, yeah, I'm just going to quickly introduce doing the formulas because that's pretty straightforward. Okay, you got to drop and swap for ionic compounds, and for molecular compounds, you just use the prefixes to tell you what number to put next to everything. It's pretty easy. Okay, writing the names is more difficult than writing the formulas. Okay, so if we're converting chemical names into formulas, essentially going backwards from what we've been doing, all right? The first step is we have to decide whether the compound is ionic or molecular. So again, we just look for the presence of a metal or not, okay? In our compound, if it's ionic, then we write the formula for the metal along with its charge. And then we write the formula for the non-metal along with its charge, and then we drop and swap, okay, in order to balance our charges. So pretty straightforward. Okay? If I've got this compound here, let's say sodium sulfide. That's an ionic compound because sodium is a metal. So I write sodium, which is Na, and sodium's charge, +1. Then I write sulfur and its charge, -2. And then I drop and swap, because dropping and swapping will balance the charges. Okay, so I take the 2, I put it here, I take the 1, I put it there, but we don't write 1s in a chemical formula, and now the compound is correct. 2 sodiums gives me 2 positive charges, 1 sulfur gives me 2 negative charges, and my compound is neutral, Na2S. I'm done. Okay, so that's the purpose of the drop and swap. Can the drop and swap be screwed up? Yes. Here's a case of it. Lead 4 oxide. What does the Roman numeral tell me about lead? It has a +4 charge. Okay? Because if it doesn't tell me that, I don't know which charge to use in my drop and swap. That Roman numeral tells me this is the lead that is 4+. All right? Oxygen is always 2-. Now, if I just drop and swap this, I'm going to get it wrong. Because it's going to say 2 and 4. What do I need to do with those numbers? Reduce. Ionic compounds only, are like fractions. If you can reduce them, you should. Okay? Molecular compounds don't. If it ends up 2 and 4 and it's molecular, you leave it that way because the prefixes told you that's how many there were. In an ionic compound, it will always be in its simplest terms.
Couldn't that completely mess up the compound though? Because you're kind of changing it from one to another?
But I'm not. It wouldn't actually go together this way. yes, the charges would be balanced, but an ionic compound is always in its simplest form, and its simplest form would be this. This lead only needs 2 oxygens to work, right? Each one of these oxygens has a charge of 2 plus. This has a charge of, 2 minus. This has a charge of 4 plus. So this way, it balances out. It balances out this way too, but it's a bigger molecule than it needs to be. Okay? All right. Ringing a bell for everybody on that one. Okay, don't pack up. Class isn't over. I'm teaching right to the end today. Okay? All right. Now, for molecular compounds, it's even easier. For a molecular compound, you just write it out. Okay? It tells you how many of everything to put in. All you have to do is remember your prefixes. So if you get this, let's say, that's molecular. As soon as I see prefixes, I know it's molecular. I don't even have to look for a metal. We know we wouldn't use prefixes in an ionic compound. All right, so I go dinitrogen, N2, trioxide, O3, done. It really doesn't get much easier than that. All right, so that's what we're going to start after our quiz tomorrow with, is doing some formula stuff, okay, and getting some practice, and then we're going to move into properties of compounds. Friday we'll do a little preparation for our lab next week, okay, and we'll move into that. So, I will post your quiz by the end of the day today, okay? Try it at home. That's what the quiz tomorrow will be like. Very similar to the one I posted today. Are there any questions?
How long is the quiz?
Oh, like 5-10 minutes tops.
Oh,
Yeah, it's short.
Sorry, could you just go over one like this? Like, at the end.
Like I give you the word and you get a formula?
No, the CISO would be like this, and then it would be phosphorus 3, and then how you figure out what this one would be.
Okay, so if I had that, okay, I would get this. So you want to know how do I get the formula right, like with the drop and swap? Okay.
Well, no, not the drum swap, sorry. No, I like how you multiply.
Oh, okay. So
Actually, that's not true.
So let's say that was my formula. Okay, so phosphorus always has a -3 charge.
That's not really cheating.
Okay? Now, since there are 2 phosphorus, that means that I have 6 negative charges, right? That means I have to get 6 positive charges from these 3 irons. So each one of these irons would have a charge of 2. So all I'm doing is going, I multiply to get this, and then I divide to get. Yeah.